In this video, we're going to look at reversing the order of a double integral. Reversing the order of a double integral. And let's just start with an example. So suppose you're asked to evaluate this double integral for y squared dy dx. And one thing you'll notice right away, and you can even remember this from Calculus 1, e to the y squared is not integrable. Now, if there was another y in front, we could integrate this with, say, u substitution. But with just a constant here, ey squared is not something that you can actually integrate. So the way we have to handle this is to change the order of integration. So now the first thing we can do is get an idea of what our original integral looked like. And first of all, say to yourself, what does this mean? Of course, this means y equal 2/3 x to y equal 8, because we know the inner integral is y. Then the outer one is x equals 0 to x equal 12. And so I just wrote those in here just to make that clear. It's y equal 2/3 to y equal 8, x equals 0 to 12. And let me draw this line, y equal 2/3. In fact, I drew it right here. That's y equal 2/3 x, like this. And then, so that's going to be the lower bound. And then we're integrating up to this one, y equal 8. Like this. And so it looks like we're integrating over this region in here. And when you look at the second bound, it makes sense because we're covered from x equals 0 to x equal 12, like this. So this looks like the correct region. But so we're going to change the order. So again, you can see from this one, it was integrated with respect to y first. We're going to integrate with respect to x first. And so when we do this, always remember when you're integrating with respect to a particular variable in a double integral, say if we integrate with respect to x first, put arrows in your region in the positive, pointing in the positive x direction. Put them in here like this. And then remember, when we integrate with respect to x first, where the arrows start will be the lower bound, and where they end will be the upper bound. Now, one thing we're going to need to do is, if we're integrating with respect to x first, we're going to have to write our lines all in terms of x equal function y. So let me rewrite this here. This can be rewritten as x equal 3/2 y, like this. And then the lower bound is going to be where the arrows start. And you can see from here, that's just going to be the line x equals 0. So this could be thought of as x equals 0. Now we can go to write our integral, starting again integrating with respect to x first. So we have still our integrands the same, except now we're going to do x first, and we're going to go from x equals 0 to x equal 3/2 y, because that's where the arrows end. And then the last integral, dy, remember the final integral is always just going to be numbers. And it's just going to be the interval, in this case on the y-axis, covered by a region. So you see our interval is from 0 to 8. Like that. And that's our integral. Again, usually books won't, when you put the bounds, they won't put x equals 0 or x equals 3/2. They'll just put 0 and 3/2 y and 0 and 8. And then, of course, you tell by the dx and dy which is first and which is second. But a lot of times I like to write this in so it's clear to everybody what's going on. So let's go ahead now, see if we can evaluate this double integral. So y equals 0, y equals 8. And again, inside here, this becomes 4y squared, integrating with respect to x. So that's going to be x, and that's going to be evaluated from 0 to 3/2 y dy, like this. And then when we put our bounds in, we'll put our bounds up here in for x, and that's going to be 4y squared 3/2 y. And then we put the lower bound x equals 0, x equals 0. That's just going to be 0. So, and let me sort of let me divide this up a little bit. So this is going to be 4 divided by 2. That gives us 2. 2 times 3 is 6. And then we're going to have ey squared y dy, like this. Now the integral is much easier to handle. We can just use u substitution. U equal y squared. Then du is equal to 2y dy. Then finally, write this as du over 2y dy. Like this. So we can substitute for y dy, we can put du. For y squared, we can just put u. And let's do that substitution. And so it'll be eu and du over 2 for these. And we could even cancel this, make this 3. And of course, when we integrate e to the u du, that's just going to be e to the u again. And it's going to be evaluated. Let me put the original back in. And go put the original function back in. This will be 3y squared from y equals 0 to y equal 8. And that's going to give us 3e. That's going to be just 8 squared. Now this lower bound, we have to be careful because we're putting a 0 into e. And so that's not going to be 0. And so this is going to be 3e, what to the 64. E to the 0 is 1 minus 3, like that. Or if you want to factor the 3 out, you could write e to the 64 minus 1. But so that's how we handle a changing of the order of the integral, the most important thing is to draw the area over which the original integral is done, then just kind of treat it like a new problem and integrate with respect to whichever variable that you need to do. In this case, we're integrating with respect to x first. And so we did that. Again, always put, if you're not sure how to do this, always put arrows in the positive direction of whatever variable you're doing first. Like in this case, dx, put arrows pointing in the positive x direction within your area. Wherever the arrow starts at lower bound, wherever they end is the upper bound. Let's take another example. Let's look at this example here. So we're asked to do this integral. And once again, you can see this is a very difficult integral to handle because we have y to the 4/3 in the denominator plus 1. So once again, we're going to change the order of integration. And again, keep in mind what we have here. According to this integral here, this is the same as y equal x cubed up to y equal 8. So let's draw that. In fact, I've already done that here. And again, remember, this is the x-axis, and this is the y-axis up here. And so the region, so it starts at y equal x cubed, again, which is this region down here, and goes up to y equal 8, this here. So the original integral covers this region here. So now we want to do x first. So just like before, you can make arrows in the positive x direction. And again, you don't need to put all these arrows, but just to get an idea of what we're doing. And so, and also just like before, we want to rewrite our boundaries as x equal function y. So here, let's rewrite this as x equal y to the 1/3. We can rewrite this way. And then again, the integral starting at x equals 0, like this. And so let's do our double integral. We're starting at x equals 0, because that's where the arrows are starting. And they're ending on this curve here, which x equal y to the 1/3. And then we need to figure out what the bounds on y are. And so y is covered from y equals 0 to y equal 8. And let's put the integrand back in here. Again, we're doing x first this time, like that. So that's going to be the integral. That's the most important part, to set up the integral. And now you're going to wonder, okay, is this going to really help? So let's see if we can evaluate this. So I rewrote this here. So let's see what happens. Integrate with respect to x first. That's going to give us y 4/3 plus 1. And then we integrate with respect to x, keeping y constant, so it's just going to give us x. That's to be evaluated from 0 to y to the third dy. And then put our bounds in. And then this is y to the 1/3. And then the lower bound would just be 0. Now here we can use u substitution to do the last integral. Take u equal y to the 4/3 plus 1. Then du equal 4/3 y to the 1/3. dy, then we can write it exactly like this so that we can substitute. So it would be 3 du over 4, 1/3 dy. So let's go ahead and do our substitutions. And this will be u here, 1 over u. So we're 1 over u, we're replacing u in place of this. And then for this, we're going to put this. I'm going to put that 3/4 out front here to make it a little less cluttered. And this will be du. This. And go ahead and integrate this. Of course, that's going to be log. 3/4 log of u. And again, I'm going to go ahead and put the original function back in. 3/4 log of y to the 4/3 plus 1 from, or the bound 0 to 8. And so we have 4/3 log, excuse me, 3/4 log of 8 to the 4/3 plus 1 minus the lower bound. We can't better check to be sure. The lower bound log of 0 plus 1. And of course, the cube root of 8 is 2. And then we're raising it to the 4th power. That's going to be 16. So 8 to the 4/3 is going to be 16 plus 1, which gives us 17. And then the log of 1 is 0. So the lower bound is going to be 0. And so that's our answer. And that's the way we always do these reverse order of integration problems. Be sure to figure out what your original domain is. Figure out what it is. Then change the order. So if in this case, we were doing y first, so we're going to change it to x. And then remember, use the same region as the original integral. Put arrows in the positive x direction where the arrows start. That's the lower bound at x equals 0. They end up here at x equal y to the 1/3. You just always have to rewrite this equation so that it's in terms of x of function y. And then now, because we made this change, even though the integral looks kind of messy, still it's much, much better because we were able to get it to the point where we could use u substitution. And that allowed us to do the integral.